reactions. We have been working towards this one for a while. Okay. So reactions. Chemical reaction is the process where the atoms of one substance are rearranged and we're forming new substances. We also know that as a chemical change. Need to make a copy of this today. All right, so you should have written in reaction and change or changes. Everybody good with that? All right. We talked back in chapter 3. It's been a while, you guys. We talked back in chapter 3 about evidence of a chemical change. And I just actually copied this slide right from that presentation. Okay. We have a temperature change. We form heat and light. I mean, think about like a fire. If you create a fire, all three of these things are happening. Absorb heat. We talked about how if you have one of those ice packs in the first aid kit, you kind of break a seal and that causes it to get cold. Color change. Again, a fire. Odor, a fire. Gas bubbles. Sometimes you can see those on like the logs. You'll see gas bubbles form on the fire. And then appearance of a precipitate. You guys did that. You made silver chloride back at the beginning of the year where you had the filter paper. You put it underneath the hood. You came back. It looked like this like colored lavender thing. Remember that? Okay. So those are all indicators of chemical change. All right, good. All right.
Nearly.
What? No?
Nearly, sorry.
Okay. Precipitate, yep. All right. So when we're doing this, we're starting with beginning things. Those beginning things are called reactants. So that's the stuff that we're starting with. And if we're talking about like that lab that you did last year, you were starting, your beginning reactant was silver, was it nitrate? I think it was silver nitrate. Yeah, it's a nitrate. And we added hydrochloric acid to that. Okay. And then you ended up with your products over here. Okay. This arrow, you either say reacts to produce or produces or yields. This is not the same yield like you have with driving. Okay. That yield means to slow down and proceed with caution, right? The yield that we're talking about is the same yield that like farmers use when they talk about their crop yields. So this strain of corn will yield so many bushels per acre. There's another definition for yield than this definition that you're used to for driving. Okay. This is a yield that we're talking about. We're making stuff. Okay. And what you made last semester was you made silver chloride and you made nitric acid. The chlorine and the nitrogen or the nitrate swap spots. And this was your silver or solid, that was your precipitate. And this was still as a liquid mixed together in there. Okay. So these are the things that you made in that reaction. All right. So these were your reactants and these are your products. And you're going to learn in this chapter how to start with these things and figure out what you're going to make over here. So that'll be sometime next week that you start doing these types of reactions. But right now I'm just showing you, okay, these are called reactants. These are called products. Okay. All right. One other critical thing that you need to remember for this, well, for the rest of the year, honestly, are these Brinkelhoffs, these diatomic elements. And we get Brinkel. Why did you change on me? Brinkel is Brinkel. That's where we get the Brinkel from. Okay. And then Hoff is the rest of it. What that means is these are diatomic atoms. So when you have them in their pure form, you're always going to write them with a subscript 0 or 2 down here. Okay. So when you have like oxygen by itself, you don't just write O down, you write O2. And then whatever else it's reacting with. So maybe some hydrogen. And then you're going to come over here and you're going to form some hydrogen peroxide. Okay. The key point is that when we say oxygen reacts with something, when you write oxygen down, you write it down like this. If we say hydrogen reacts with something, you're going to write it down like this. So these are Brinkelhoffs. When they are not combined with anything else, they're always combined with one of themselves. Got it? All right, moving on. We also have indicators of phase. So what is this stuff starting out as? Well, when we were doing that silver chloride, that was in a solution with water. So we're going to say aqueous there because we take that powder in the back and we mix it up with some water. And then your acids are always aqueous. Then we ended up, no, we didn't start with that. We started with nitrate, didn't we? We formed this. Sorry. That formed a solid here. And then the H formed nitric acid with a nitrate, and acids are always aqueous. Okay, so they just swap partners. Do you see that? The silver goes with the chlorine, the hydrogen goes with the nitrate. But remember, your cations are always listed first. Your positive ions are always listed first. All right, so that's how we're indicating phase. This indicates that you have a solid form. That was your precipitate. That was a powder that was on the filter paper when you were done with that reaction. All right, chemical equations. They are going to show that matter is conserved during a reaction. So we start out with a skeleton equation that lacks that information. Then we go through and we follow the conservation of mass law. And we do that by making sure that our reactants and our products are equal on both sides of the arrow. So we're making sure that matter is conserved during a reaction. We're showing that with an equation. And we're doing that in order to get the mass law, conservation of mass law. Making sure that we have our reactants and our products equal to one another. Happy times, happy days, everybody good? Need more time?
Not the skeleton equation. Uses chemical instead of word to indicate the reacting products. I didn't catch that one on the left side.
This is the same slide. I haven't changed it. This one? Oh, I skipped that one. Chemical formulas.
Okay.
All right, good? Pretty good then? All right, now, in order to balance these equations, you have to find the correct coefficients. The coefficient is a chemical equation that's written in front. We don't write ones. And we're going to balance the equation to the lowest whole number ratio. All right, step 1, you're going to write the skeleton equation. That's the formulas. Step 2, you're going to count the atoms of the elements in the reactants and then the products. Then you're going to change the coefficients. You cannot, naughty, 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 don't even think about it. You cannot change subscripts. Come over and smack your hand with a ruler. No, I'm just kidding. I'm not going to smack your hand with a ruler. You know that by now. Okay. But you cannot change the subscripts. I'm jumping up and down. I'm screaming. I'm yelling. Can you see me in your head do this? You can visualize that. Yes. Okay. You can only change coefficients, and those coefficients have to be written in their lowest possible ratio. And I usually take a point off. Like if it's a 5-point thing, I'll take a point off if you don't do that. Okay. So you got to reduce it down. All right. These are polyatomic ions. This is from the old book. Now we have these on the back side of your periodic table. So count your polyatomic ions as a single unit if they're unchanged on both sides. I'm going to show you what I mean by this as we go through. Okay. Leave uncombined elements, so elements by themselves, leave those to the end to balance. Hydrocarbons often have to be doubled, and I'll show you kind of a hint with that once we get into those. Remember, odd and even, you're going to double the odd, okay? Because if you have an even number, your answer is always what? An even number. If you have an even and an odd, your answer is always an even number. The only time that you have an odd answer is when you have two odd numbers multiplied together. So if you're trying to get, if you've got an even number on one side, if you've got an even number on one side and an odd number on the other side, you're never going to get that odd. You're never going to get that even number odd. You can't do it. You can't multiply that even number by anything and get it odd. It's a whole number. Okay. So the only way you're going to be able to do that is by doubling the odd number. Does that make sense mathematically? Kind of the rationale there. And then water can be written as HOH. And why that's important is going back up to this, because OH is a polyatomic ion, despite what a few of you wanted it to be on your test yesterday. We won't go back there, right? All right. So here we go. Here's our first equation. And this is the way we're starting out. We're going to be giving you equations like this. We may say to you, mercury 2 oxide yields mercury plus oxygen. And you're going to need to know how to write mercury 2 oxide and mercury and oxygen. Why does this have a 2 and this not down here? Right. This is a Brinkelhoff. This isn't. Okay. All right. So that being said, let's learn how to balance equations. All right. First of all, I tell you to start by drawing a line below the arrow to separate your products from your reactants. Then I'm going to write an HG here and an O. I'm going to write the same inventory over here in the same order. No matter how it's written over here, I'm always going to keep them in the same order for the inventories because it's easier for your brain to be able to go across the same line than to be going up and down and back and forth. And it's not hard with 2 things, but when you get 4 or 5 things out there, it just makes it easier for you. Okay? All right. Then I'm going to inventory. I've got one of these over here. I've got one of these over here. On this side, I have 1. On this side, I have 2. I'm going to compare my inventories. If all of the numbers are equal for each species, so if this is a 1 and this is a 1 and this is a 1 and this is a 1, we're done. But that's not the case. I've got to get this guy up to a 2. So I'm going to go back to my hints. Even and odd, I'm going to do what? What did I say? Even and odd, double the odd. Okay, so I'm going to double this guy, but I do not do this. Okay, I cannot squeeze that coefficient in here. No, 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 jumping up and down, screaming. Okay, that coefficient has to go out in front of that entire molecule, or formula unit in this case. But that's not only going to affect my oxygen, it's also going to affect my mercury. So I've got to go down here and reestablish my inventory. Now, that took care of my issue with oxygen. But what did it create as a problem in the process? Problem with the mercury. So now I need 2 mercuries. I'm going to put a 2 here. Go back and double check my inventory. Everything's balanced now. So that is a balanced equation. Does that make sense?
How come is there only a 2 as a subscript on oxygen because it's a Brinkle?
Yep. Now these, there's no subscripts because this is a +2 and this is a -2. Now, how did I know that this was a +2? Because oxygen's always a -2. So if oxygen's a -2 and these are in a 1-to-1 ratio, this has to be a +2. So because they already cancel each other out, there's no subscripts down for these.
Only change the coefficient, you're not changing the subscript.
Correct. Okay. So here's our next one. So I'm going to start by dividing. Now, this is going to have several different of those hints in play here. All right. When I start writing down my inventory, I've got sodium. I have OH here. OH is one of those polyatomic ions. Do I have OH on the other side anywhere? But remember, one of the last hints was, right, I can rewrite this as HOH. And now I have an OH over here. See that? If the polyatomic ion is held together on both sides, I can write that down together as my inventory. Okay, and I'm going to explain to you why I want to do that in just a second. Let me get through this first, and then I'm going to come back to that. All right, now I've got my hydrogen, and do you see the SO4 over here is the same as the SO4 over here? So if that SO4 is unchanged, I can write that out as SO4. Now I'm going to write my inventory down. I'm going to keep it in the same order that it appears in this list. Even though it's not in the same order written up here, I want to keep these the same so that when I'm comparing those quantities, I'm going across in the same line. All right. Now let's look at why I wanted to redo that OH and keep it together. Okay. If I didn't, I would have to add these oxygens up. I would have one here. Why are you not writing now? I get one thing working and then everything stops working. I'm all froze up now. So picking up here, we had our sodium, we had our hydroxide, we had our hydrogen, we had our sulfate. Over here, same deal, Na, OH, even though it's not written in the same order, I want to keep it in the same order as the chart. Okay, now, if I had not broke that out, I would have to add these oxygens up, and I'd have 5 here. So 1 plus 4 is 5. 4 plus 1 is 5. Oh, they're balanced. Great. Well, some of this other stuff isn't, though. Okay. So, for example, I've got 1 sodium, I have 1 hydroxide, I have 2 hydrogens, and I have 1 sulfate. But, Lippy, there's a 4 out here. That's still 1 sulfate. How would I denote it if I had more than 1 sulfate? I would have to have parentheses and another thing out here. So I've got 1 sulfate there. All right, coming over to this side, I have 2 sodiums. Remember, we had rewritten this as HOH. I have 1 OH. I have 1 hydrogen, and I have 1 sulfate. So I've got to get this guy in line. So I'm going to find my sodium. I'm going to take my even and odd, or even and odd, and what am I going to do? Even and odd, double the odd. Okay, so I'm going to put a 2 out here. That not only affects my sodium, it also affects my OH. So now I've got 2 of those. Okay. So I go back over here. I need 2 hydrogens and I need 2 OHs. What do? Yep, I'm going to put a 2 here, and that's going to take care of that guy and that guy. Do you see how keeping these polyatomic ions together balances this much more quickly? Okay. Otherwise, you've got to go back and go, okay, I've got 2 here plus 4, that's 6. And then it's just a mess. So keeping those polyatomic ions together, if you can, really helps out. All right. Any questions on that guy? All right. Let's try to look at another one. Here we go. All right. So here I have lead. I have nitrate here. The nitrate is the same on both sides, so I'm going to keep that together. I've got potassium, and then I've got chromate here. And that chromate is the same on both sides, so I can keep it together.
What if you would have like phosphate and then phosphite on this?
So you have to break it out. It has to be the same on both sides. But a lot of times it is, and I'm just telling you guys, like it is. It used to be that I would have folks come in and they had physical science first, and then they came in. Physical science, for some reason, a lot of times doesn't teach it like this. They make them break this out and go, okay, I've got 6 oxygens here, and I've got plus 4 oxygens here. And then they go and start monkeying with trying to balance this. And If you keep those polyatomic ions together when you're balancing, Mr. Schramm's nodding his head, if you keep those together, it balances like a breeze. But if you break them out, it is painful, you guys. All right, let's look at balance or where our inventories are right now. Okay, for my lead, I've got 1. How many nitrates do I have? 2. So this is what I was talking about. If you've got more than one of those polyatomic ions, it's going to be in parentheses and you're going to have a subscript outside. All right. My potassium is 2. And then how many chromates do I have on this side? 1. Okay. So see if you can get this side inventoried. Did you get your inventories down? What'd you get for everything? Just straight ones? Yeah? Easy enough? All right. So we got that done. Now we need to balance this. Okay. Can you see pretty quickly what you've got to do to get this balanced? All you have to do is put a 2 here. That's going to get a 2 here and a 2 here. Now, if you had broken those out into oxygens and nitrogens and chromiums, like you're comparing, you've got like a whole bunch of stuff there that you've got to add up together and break apart and figure out. And I'm telling you guys, it is so much easier. Like you'll be like, oh, that was easy. All right, let's look at the next one here. I think this is the last one too. Yep. All right. So here I've got my H on this side. I have sulfate on this side, and it looks the same over here. So I'm going to keep that together. I have boron, and then I have OH here. I don't have OH here yet, but what can I do to get it? Right. I'm going to replace this with HOH. And now I have my OH. Write down my inventory in the same order. See if you can balance this. Get your inventories written in and then see if you can get it balanced. Okay, thanks. Just stay in here until there's no sense of going all the way downstairs. Your attendance is already cleared for you, so. All right. I need to get, I'm going to start, put a 2 there. That's not going to help. Because I'm still going to have issues with my oxygen or my OHs here. So I get a 3. If I do a 3 there, that's not going to help. So I'm going to start by putting a 6 here. It's going to be 6 of these and 6 of these. And then my sulfates, I need 3 of those. So by putting a 3 there, that's going to give me 3 sulfates, and it's going to give me 6 of those, which is good. That's what I needed. And then my borons, I need 2 of those. So I'm going to put a 2 there, and that's going to give me 6 of these. There we go. That's how you get it balanced. All right. In your packet, you should have 9-1 that you're going to be doing for homework. Okay. So 9-1 starts out. Oh, I have types of reactions on here too. We have time for, yeah, we got time for that. Okay. So 9-1 starts out the same way that I have been doing this other stuff, except we got to talk about different reaction types here. Okay. And then it gets into the words where you've got to write the formulas out, and that's going to be a little more painful, but you guys are you need to get used to doing it. I'm telling you, it's coming. Okay. So let's talk about types of reactions then. All right. When we are looking at types of reactions, we are looking at where we have the first type here is called a synthesis reaction. It's where you're taking two things and you're bringing them together to make one molecule. So synthesis, you take two items, two separate things, and you bring them together to make one. So that's a synthesis. It's kind of like marriage. Okay? You got two people, they get married. All right? So if we're looking for an example of that on your homework for tonight, that is going to be number 2 on your homework, where we have CO plus oxygen, and that is making CO2. So that's an example of a synthesis reaction. All right. So that you're going to write down synthesis. You'd write down a capital S, and that is a synthesis reaction. All right. If that is like marriage, what does the next one look like it would be? Divorce, right? Okay. So here we've got one thing and we're breaking it into two. This is the absolute easiest one to identify because what you have to do is you look down and you see there's no plus signs in any of the reactions. So find an example there in the homework for tonight where you've got that going on. You don't have a plus sign for your reactants. Where do you have that? Number 4. So if you look at number 4 there, number 4, you're starting out with NaNO3, and it is breaking apart into NaNO2 plus O2. And this is one where you were asking me if it was different, the polyatomic ion was a little different on both sides. Yeah, you're going to have to break all of these out. You can't keep that polyatomic ion together. So in your inventory, you're going to have a nitrogen or sodium, you're going to have a nitrogen, and you're going to have oxygen. So you can't keep the polyatomic ion together in that case. All right. So that is like number 4 on your homework for tonight. All right, let's look at the next one. The next one, this is where you have two people in a relationship and somebody comes along, and now they're sitting on the, they broke up and now they've got somebody else and this one's all Lonely Hearts Club. They're sitting there eating their tub of ice cream in their pajamas and watching sad romance novel movies and crying the whole time. Okay, you got that visual then? Okay. All right, so let's see if we can find an example of that one on here. Yep, number 1 on your homework is an example of that. Number 1, we've got sodium. Sodium's there. He's like, oh, I'm all that. And we've got our HOH over here. And guess what's going to happen to lonely old H? He's going to have to go over here and sit and eat its ice cream. Be sad. Because Na is going to hook up with OH. Tub of ice cream, jammies, box of Kleenex, watching romance movies. and crying. Yes? Good.
Wait, no.
No?
Wait, no.
Well, maybe H is happy. He's like, I'm done. Yeah. OH can deal with that thing now. I don't want anything to do with it.
Is this combustion or is it single replacement?
This is single replacement.
Oh yeah, that makes more sense. So what's
We'll get to combustion in a minute.
Oh, okay.
Okay. So this is single replacement because he's single now. Now, you think that was fun? We're getting like a Maury Povich kind of thing going on. Jerry Springer, whoever's the person that does those shows nowadays. But yeah, so see what's happening here. Boom, chicka, wah, wah. Trying to find an example of that. That is number 3 on your homework. This is a double replacement reaction. Okay. A was with B. C was with D. But A is now with C. And or A is with C, yeah, and B is with D. Okay. Messed up Maury Povich, Jerry Springer. You are not the father, you are the father. Those shows. You got them. They're screaming on stage, they're throwing chairs, they're angry. All right. So that is number 4 on sorry, not number 4. It wasn't number 4, it was number 3. That is number 3 on your homework for tonight. So that is an example. And we're going to get into more of those examples tomorrow. Now, Ray was asking about combustion. So combustion reactions are any reaction where you have oxygen as one of your reactants. And sometimes it's this guy, sometimes it's this guy. So where oxygen is one of your reactants, so it could either be, so this has 2 identities. It goes as a synthesis, or it could also be a combustion. But again, an easy one to identify because you go down the row and you go, oh, oxygen's a reactant, combustion. Oxygen's a reactant, oh, combustion. So it's an easy one for identification.
Wait, so what about number 2 then?
Number 2 is a combustion reaction, and it is also a synthesis reaction. Just like I am a mom and I'm a teacher. I have 2 roles. So you can either identify me as a mom or you can identify me as a teacher.
Oh, so both work.
Both work.
Okay.
Yep.
Okay, that makes it easier.
Yep. Good. So you can give me either answer. My answer key has both on it. And I will accept either one for full credit. Full and happy credit. All right. So you guys are going